Hello everyone. I'm Dr. Michael, and we're continuing our new series called Celestial Chronicles. Stars are usually born in families, in open or globular clusters, and many of them can spend their entire lives there, but sometimes, they don't. Astronomers have long known that globular clusters, those creative gatherings of old stars, gradually lose some of their members over time. These runaway stars enrich the halo of the Milky Way. And now, an international team of scientists has traced these stars back to the beginning of their journeys, giving us insight into the dynamic and chemical evolution of our galaxy.
Globular clusters, as ancient as the galaxy itself, constantly lose stars that drift away and join the general stellar field of the Milky Way. It's quite possible that these escapees significantly influence the galaxy's halo. If a star left its parent cluster long ago, its origin can be traced by analyzing certain chemical composition markers, such as nitrogen abundance. In a recent study, a team of scientists aimed to establish dynamic connections between nitrogen-rich stars in the Milky Way, recently identified by the LAMO survey, and existing globular clusters in the Milky Way. By analyzing the characteristics of proper motions along with metallicity, they managed to identify 29 potential parent clusters for 15 nitrogen-rich field stars. Some of these stars may even be linked to accretion events in the Milky Way. On the other hand, if a star recently left its globular cluster due to tidal forces, it still retains the kinematic properties of that cluster. Based on spatial location analysis, proper motions, and positions on color magnitude diagrams, more than 1,600 additional candidates were successfully identified near 6 globular clusters. The spatial distribution of these additional candidates confirmed the effectiveness of searching for structures beyond the original birthplace and pointed to the possible presence of long stellar streams. Among 95 additional candidates with spectroscopic data on radial velocities and metallicity, 54 were confirmed as globular cluster escapees, as they share similar properties with their parent clusters. These additional candidates are ideal targets for follow-up spectroscopic observations. Once a statistically significant amount of spectroscopic radial velocities and metallicities becomes available, the dynamic evolution of globular clusters, including mass loss, rotation, and evolution over time, can be carefully studied. This, in turn, will provide insights into the evolution of our own galaxy.
Globular clusters contain millions of stars. But each one is unique, fascinating, and one of a kind. We might even imagine that each star has its own personality. Take, for example, the lithium-rich Cepheid V708 Carina.
An international team of astronomers has conducted a comprehensive spectroscopic analysis of V708 Carinae, revealing its unusual chemical composition. This star, located about 4.4 kiloparsecs from the Sun, is a lithium-rich supergiant, which is a rare characteristic for such stars. V708 Carinae has a mass of approximately 12 solar masses and a pulsation period of 51.4 days. The spectroscopic data, collected using the high-resolution spectrograph at the Southern African Large Telescope, shows that the abundances of various chemical elements in V708 Carinae correlate with their condensation temperatures. Elements with higher condensation temperatures appear in lower abundances, an unusual feature for classical Cepheids. The researchers suggest that this peculiar chemical composition is due to a gas-dust separation process in the star's envelope. This phenomenon is similar to what is observed in other types of stars, such as Lambda Boötes and W Virgo stars, as well as asymptotic giant branch stars. In these stars, refractory elements form dust particles that are swept out by the star's radiative pressure, leaving behind a gas enriched in volatile elements. Additionally, V708 Carinae shows a strong emission of hydrogen alpha, indicating the presence of a gaseous envelope. This supports the theory that the star's atmosphere has been influenced by past interactions with its circumstellar material. These findings not only deepen our understanding of the chemical peculiarities in classical Cepheids, but also provide insights into the processes that shape their evolution. The study of V708 Carinae is a testament to the continuous advancements in astronomical research, uncovering the mysteries of the stars that light up our universe.
M-dwarfs, dim red stars, are plentiful in our galaxy. Lately, astronomers have been discovering planets orbiting them in droves, and it's no longer surprising. Many of these exoplanets around red dwarfs even lie within the habitable zone of their stars. It seems like the perfect recipe for life to flourish and evolve. But there's a catch: red dwarfs produce powerful flares that can have a major impact on the possibility of life forming on planets at close distances. Meet Teegarden's star, with its remarkable planetary system.
Teegarden star, located about 12.5 light-years away in the Aries constellation, has been a subject of intense study. Using advanced instruments like CARMENES, ESPRESSO, Maroon X, and HPF, researchers have discovered a third planet orbiting this star.
Through meticulous reanalysis of 346 nightly bin radial velocity data, we identified a new planet, named Teegarden Star D. This planet has an orbital period of 26.13 days and a minimum mass of 0.82 times that of Earth. However, it lies outside the habitable zone of Teegarden star. In addition, a signal at 96 days was observed, aligning with the star's rotation period. Another signal at 172 days remains a mystery. It could be due to stellar activity or possibly another long-period planet.
Interestingly, the data also showed very long-period variability, suggesting an activity cycle. This means Teegarden star could be more dynamic than previously thought. The Speculoos telescopes revealed several stellar flares from Teegarden star. These flares, which are sudden bursts of energy, provide key insights into the star's behavior and potential impacts on its planets.
We observed 13 stellar flares, including 10 single-peak flares and a multi-flare region with 3 peaks. These observations help us understand the frequency and energy of such flares, which could influence the habitability of surrounding planets.
This research is crucial for our understanding of the architecture of nearby planetary systems, especially those that could be candidates for further atmospheric studies.
Uranus, a magnificent beauty, the pride of the solar system, is remarkable not only for its rings and the extreme tilt of its axis, making it appear to roll along its orbit, but also for its strange atmosphere filled with fascinating gases like methane. You might think, what could possibly be interesting about that? Well, listen to our story about Uranus.
We are exploring the remarkable complexity of the planet Uranus thanks to groundbreaking research from the Department of Astrophysics at the University of Zurich. Our journey begins with a critical question: what lies beneath the clouded facade of Uranus? While its primary composition remains a mystery, recent studies have shed new light on the planet's internal structure, revealing that it is not fully convective. This means that Uranus doesn't follow a simple, uniform temperature distribution as previously thought. Researchers have developed a new method for interpreting empirical models of the planet's structure, allowing them to identify non-convective regions and understand how uncertainties in Uranus's rotation period and winds impact its composition and temperature profile. Their findings are astonishing. It appears that there are non-adiabatic zones within Uranus, leading to much higher internal temperatures, reaching tens of thousands of kelvins, and a greater concentration of heavy elements compared to standard models. These non-adiabatic areas significantly affect the planet's temperature profile and overall composition. Diving deeper into Uranus, we discover a complex structure where convective and non-convective zones coexist. This layered composition has profound implications for our understanding of Uranus and other similar exoplanets in the galaxy. One of the key discoveries is the impact of Uranus's rotation period on its predicted composition. A faster rotation period results in higher temperatures in the inner layers and a greater concentration of heavy elements. In contrast, the depth to which winds penetrate the lower atmosphere of Uranus, up to 1,000 kilometers, has only a minor effect on the temperature profile. The study emphasizes the importance of measuring Uranus's gravitational field and determining its rotation period to reduce uncertainties. Continuing this research will be crucial for understanding the planet's formation and evolution.
Who would have thought? It seemed like Uranus's atmosphere was practically the perfect example of an adiabatic process, straight out of a high school physics textbook. Yeah. And on that note, it's impossible not to mention the stunning image of Uranus captured by the James Webb Space Telescope. Just look at this beauty. Uranus is a stunner, and so is Webb. Now, let's continue our journey into the galaxy, into the realm of hot subdwarfs.
Scientists have made significant progress in understanding pulsating hot subdwarf B stars. These are bright, helium-burning stars that have shed their outer hydrogen shells during interactions with close companions. In percentage terms, there aren't many pulsating subdwarfs, and they are mainly discovered by chance when analyzing various sets of photometric data. Using data from the Gaia, Kepler, and TESS missions, researchers have been able to create a comprehensive catalogue of these stars. They discovered 61 new and 20 candidate pulsating subdwarf B stars, offering new insights into stellar evolution and binary star systems. Hot subdwarf B stars, SDB stars, are thought to have a helium core surrounded by a thin hydrogen envelope with a mass less than 0.02 solar masses. The average mass of these subdwarfs is estimated at 0.47 solar masses, enough to ignite helium after the star has burned most of its hydrogen fuel. SDB stars are compact objects with effective temperatures ranging from 20,000 to 40,000 Kelvin. The evolution of these stars involves substantial mass loss, apparently due to interactions with a companion star in the late red giant stages. As a result, the helium core is exposed, surrounded by a thin hydrogen envelope that can no longer sustain hydrogen burning. For about 100 million years, SDB stars continue burning helium in their cores, gradually transforming it into carbon and oxygen. This leads to the SDO phase, oxygen-rich subdwarfs. Eventually, they all become white dwarfs, enriching the surrounding cosmos with carbon, oxygen, and other elements synthesized in their cores. In 1997, Kilkenny et al. Discovered rapid pulsations in hot SDB dwarfs, with periods ranging from 60 to 800 seconds, during which their brightness varies by fractions of a percent. Later, another class of pulsators was discovered, with a slightly different temperature and pulsation periods that can last several hours. With the launch of the Kepler mission, and especially TESS, the study of SDB pulsators received a major boost. However, the Gaia mission played a key role in identifying subdwarfs, providing precise measurements of their positions and movements. Using TESS data across the sky, researchers identified 2,371 candidate pulsators. After careful analysis using statistical methods, the total number of known SDB pulsators expanded to 317 within distances of up to 500 parsecs. This research not only helps us understand the life cycle of stars but also expands our knowledge of stellar atmospheres and internal structures. New missions like Plato and the Large Synoptic Survey Telescope, LSST, promise to expand our knowledge even further, helping to create a more complete sample of hot subdwarfs.
That's all for today. Stay with us to learn more about exciting discoveries. Until next time, keep looking up with us. The sky is big enough for everyone.